This videotape deals with solving simple inequalities. Before we actually start solving inequalities, let me review the basic inequality symbols for you. Okay, this symbol is read is less than. For example, 3 is less than 7. This symbol is read is less than or equal to. For example, 4 is less than or equal to 10. In this case, the less than is really holding. 4 is less than 10. But this means is less than or equal to. Either less than or equal to. If either one holds, then this would be a true statement. 4 is less than or equal to 10 because 4 is less than 10. But I could also write 5 is less than or equal to 5. In this case, it's the equality that holds. 5 is equal to 5. Therefore, it is less than or equal to in the sense that it is equal to. Just one of these has to hold. Okay, this symbol is read is greater than. Seven is greater than 3. Okay, notice that this is just the reversal of the inequality that we have over here. Here we had 3 is less than 7. Well, if 3 is less than 7, it stands to reason that 7 is greater than 3. The inequality can be read left to right. 3 is less than 7, or right to left. 7 is greater than 3. And we also have a symbol for is greater than or equal to. For example, 10 is greater than or equal to 4. Just like we had before, 4 is less than or equal to 10. Or is the key word here. It's got to be greater than or equal to. As long as one of those is true, then this is a true statement. 10 is greater than 4, so it's certainly greater than or equal to 4. 5 is greater than or equal to 5, because 5 is equal to 5. Okay, now, it's helpful to visualize inequalities by looking at the number line. Okay, let me put down a number line here for you. This is 0, or origin, and we have +1, +2, +3, +4, and so on. And of course, we can leave out the plus signs for the positive numbers. And here, -1, -2, -3, -4. Okay. Now, 2 is less than 3. Okay, we know this is true. Geometrically, this means that the point that represents the number 2 on the number line here is to the left of the point that represents the number 3. 2 is less than 3 if 2 is to the left of 3 on the number line. Similarly, 3 is greater than 2 because 3 is to the right of 2 on the number line. Okay, so a number being, if A is less than B, then A is to the left of B on the number line. If A is greater than B, A is to the right of B on the number line. Okay, now let's see how that works with the negative numbers. The positive numbers most people have no difficulty with. Let's look at the numbers -2 and -3. While 2 is less than 3, -2 is to the right of -3. Therefore, -2 is bigger than -3. Similarly, -3 and -2. -3 is to the left of -2. -3, therefore, is less than -2. Okay, study this idea so that you understand it. Okay, positive numbers, 2 is less than 3, but with negative numbers here, -2 is greater than -3. The whole idea, a number is less than another number if it appears to the left of it on the number line. Okay, now let's look at some simple inequalities and try to graph, we're going to sketch the graph of these inequalities. That is, we're going to try to indicate on the number line all values of x that make the inequality a true statement. Let's start with x greater than or equal to 3. Okay, if we wanted to graph the solution set for this inequality, here we have 0, 1, 2, 3, 4, and so on, minus 1, minus 2. All right. X greater than or equal to 3. Where are all those numbers that are greater than or equal to 3? Well, to begin with, we notice that 3 makes this a true statement. 3 is greater than or equal to 3. So we would certainly want 3 to be included. And then we would want anything larger than 3. 4 is greater than 3. 3.5 is greater than 3, and so on. So we can indicate this in this manner. We fill in a circle here at 3 to indicate that 3 is acceptable, and then we move off to the right like this. Okay? This indicates that all those values that make this a true statement are all those numbers 3 and up. Okay, starting at 3 and moving off to the right. That is, starting at 3, all those numbers 3 and larger make this a true statement. Okay, now suppose we want to look at the inequality x is less than 2. Here's 0, 1, 2, 3, minus 1, minus 2, and so on. Okay, now we don't, what values make this a true statement? Well, 1 is certainly okay. 0 is okay. We don't want 2 because 2 is not less than 2. This doesn't say less than or equal. It just says less than, a strict inequality. 2 is not less than 2. But 1.9 is all right. 1.9 is less than 2. 1.99 is less than 2. To indicate this, what I'm going to do is to put a circle, okay, around 2. I'm not going to fill it in the way I did over here, where 3 was a possible answer. I'm just going to leave a circle here, not filled in, and then indicate all those values to the left. Okay, here is the graph of this inequality. Okay, not 2, but everything less than 2. Okay, and this indicates it. One more time, notice that 3 is filled in because 3 is an acceptable answer. 3 is equal to 3, therefore it is greater than or equal to 3. But 2 was left out because 2 is not less than 2. Okay, let's look at an inequality in this form. 2 is less than or equal to x, less than 5. Now let me explain what a double inequality like this means. This means 2 is less than or equal to x, and x is less than 5. Now, 2 is less than or equal to x, I find a little cumbersome to work with. I prefer if I have my variables on the left. Okay? But 2 less than or equal to x can be reversed. Instead of reading from left to right, you can read from right to left here. If 2 is less than or equal to x, then it stands to reason that x must be greater than or equal to 2. So what we have here is that x is greater than or equal to 2 and x is less than 5. So just make sure you understand this idea. This is similar to saying if 3 is less than 7, then 7 must be greater than 3. It's like each inequality has sort of a dual inequality that goes with it, reading it in the opposite direction. If 3 is less than 7, then reading it the other way, 7 is greater than 3. If 2 is less than or equal to x, then x must be greater than or equal to 2. Okay? Whereas we want all those values of x that are both greater than or equal to 2 and less than 5 at the same time. Remember, there is the word and here, not or. We want it to be greater than or equal to 2 and less than 5 at the same time. Well, where are those numbers? Quite simply, those are the numbers that are between 2 and 5. For example, 3 satisfies these conditions. It's greater than or equal to 2, and at the same time, it's less than 5. Okay, so let me indicate the solution set here. 0, 1, 2, 3, 4, 5, 6, and here are the negative numbers, and so on. Now, greater than or equal to 2 and less than 5. I want everything that's greater than 2 and less than 5 at the same time. Now look, greater than or equal to 2 means 2 is an acceptable answer here. 2 certainly satisfies the condition that it's greater than or equal to 2 because it's equal to 2 and it's less than 5. Now you can move on up till 5. Now 5 does not work. 5 is not less than 5, but 4.9 is okay. So we're going to stop just short of 5. I'll indicate this with a circle here that is not filled in. And the answers are all those values from 2 until 5, including 2, but excluding 5. All those values between 2 and 5, including 2, the left endpoint here, or the left lower bound here, and excluding 5. In other words, notice how you can go from this point here right to the graph. I want all those values of x between 2 and 5, including 2 because of the less than or equal to sign here, meaning 2 is acceptable, but excluding 5. For 5 to be filled in here, there would have to be a less than or equal to symbol over there. Okay, now we are interested in solving more complicated inequalities than, say, x greater than or equal to 3 or something like that. We would like to solve things like this. 3x plus 4 is less than or equal to 10. We would like to look at something like this and immediately be able to figure out those x values that make this a true statement, okay, and those x values for which it is not true. Okay, it is not true all the time. For example, if x is equal to 1, we would get 3 times 1 plus 4. We get 3 plus 4, which is 7, and that is less than 10. But if we, let's say, x equal to 3, we would get 3 times 3 plus 4, which is 9 plus 4, or 13. And that's certainly not less than 10. That's greater than 10. Okay, so we see that for certain x values, the value is going to be less than or equal to 10. Other values, it's not going to be. We want to know for which values, okay, of x will this inequality be a true statement. Okay, and the procedure for finding those x values is very similar to solving the equation 3x plus 4 is equal to 10. Okay, there are slight variations, but basically what we want to do is isolate x the same way we do when we solve an equation. Okay, now we know if we were going to solve an equation, 3x plus 4 equals 10, we would subtract 4 from both sides. Let me show you how we would do it. Okay, we would subtract, if we had the equation 3x plus 4 equals 10, we would subtract 4 from both sides, and we would get 3x equals 6, then divide both sides by 3, and we would get x equals 2. Okay, what we have here, though, is an inequality, not an equation. And the question is, can we do exactly the same kind of procedure? Well, almost. Okay, there are certain restrictions, and we're going to go into them right now. When we're finished, we're basically going to we'll have a set of rules which will enable us to solve inequalities. Okay, now I would like to start with an inequality, which is true, and see what we can do to it and still maintain a true inequality. Let's start with the inequality minus 2 is less than 1. The number minus 2 is certainly to the left of 1 on the number line. Okay, let's see what would happen if we add 2 to both sides of this inequality. Okay, then we would have minus 2 plus 2 on the left, and we would have 1 plus 2 on the right. In other words, to the minus 2 on the left, we would add 2, and to the 1 on the right, we would add 2. The left would become 0. The right would become 3. And we notice that the inequality that results is also true. 0 is less than 3. It is also a less than inequality. 0 is less than 3. So apparently, if we add the same number to both sides of the inequality, we get an inequality which is also true And if the original inequality was a less than inequality, so is the one that we have here. Okay, let's try some other things. Okay, let's start with the same inequality. Minus 2 is less than 1. And this time I would like to subtract 1 from both sides of the inequality. I'd have minus 2 minus 1 and 1 minus 1. Minus 2 minus 1 gives me minus 3. 1 minus 1 is 0. And the original inequality was a less than inequality. And what we have here is also a less than inequality. Okay, apparently subtracting, say, the same number from both sides of an inequality gives you an equally true inequality. If you started with a less than inequality, this is also a less than inequality. Minus 3 is still less than 0. Okay, now let's try multiplication. We start with minus 2 is less than 1, and I would like to multiply both sides of the inequality by the number 3. But I would also like to try multiplying both sides of the inequality by minus 1. Okay. Turns out there's a difference between multiplying both sides by a positive number and multiplying both sides by a negative number. Let's see. If we multiply both sides of the inequality by 3, we get minus 2 times 3 on the left, 1 times 3 on the right. Here we have minus 6 and 3. And of course, minus 6 is still less than 3. This was less than, and this result is still less than. Okay. In fact, we may as well multiply. Let's multiply also by minus 3. I don't want you to think that I picked the number minus 1 because it was something special. I'm going to start with the same basic inequality. Minus 2 is less than 1. And I'm going to multiply both sides now by minus 3. Okay, minus 2 times minus 3, 1 times minus 3. Okay, on the left now I have plus 6, and on the right I have minus 3. And we all know that plus 6 is larger than minus 3. The positive numbers are to the right of the negative numbers on the number line. Plus 6 is greater than minus 3. So apparently, multiplying by a negative number seems to have reversed the direction of the inequality. Where we had before minus 2 is less than 1, when we multiplied by a positive number, okay, we kept an inequality which was a less than inequality. This was less than, so was this. But when we multiplied by a negative number, okay, where we started with a less than inequality, we wound up with a greater than inequality. Okay, now I haven't written down the rules for division, but division is, after all, a form of multiplication. Instead of multiplying by 1/2, you can divide by 2. Okay, so anything in division can be thought of as a type of multiplication. Turns out the rules for division are the same as the rules for multiplication. Okay, let me right now summarize these rules for you. And this will explain how you go about solving inequalities. Okay. When solving an inequality, follow the same procedures as in solving an equation, except if you multiply or divide the inequality by a negative quantity reverse the direction of the inequality. Or we can just say reverse the inequality. Okay, the key words here would be if you multiply or divide by a negative, then you reverse the direction of the inequality. When solving an inequality, follow the same procedures as in solving an equation, except if you multiply or divide the inequality by a negative quantity, you must reverse the direction of the inequality. Okay, so let's go over the idea. When you want to solve an equation, you know it's perfectly okay to add or subtract the same number from both sides of the equation, or to multiply or divide both sides of the equation by the same non-zero quantity. You will get an equivalent equation. With inequalities, if you want to add the same number to both sides, that's fine. If you want to subtract the same number from both sides, that's fine. But when it comes to multiplication or division, okay, if you multiply or divide both sides of an inequality by a positive number, fine. But if you multiply or divide both sides of an inequality by a negative number, you must reverse the direction of the inequality. Okay, that's basically where it differs from solving an equation. When you multiply or divide by a negative quantity, that's when you have to reverse the direction of the inequality. Okay, and the rest of this videotape is going to deal with solving inequalities using this rule. Well, let's start with the first example that we had earlier, 3x plus 4 less than or equal to 10. Okay, now once again, we would like to isolate x, just as when we're solving an equation. Okay, we're going to be following the rules of inequalities. We can subtract 4 from both sides. That's no problem. Remember, addition and subtraction, even if you see a minus 4 or something, don't worry. Addition and subtraction, that's fine. You can keep the same direction of the inequality. And we get 3x less than or equal to 6. Okay, then you can divide both sides by 3, which is a positive number, and you get the answer x less than or equal to 2. This is the solution, and of course you can graph this solution. We have all those values of x, 2 and smaller. Okay, that's where all the x values are that make this original inequality a true statement. You remember earlier we tried x equals 1 and that worked, and x equals 3 did not work. Well, here we see why. To make this a true statement, the x value that you substitute in would have to be 2 or smaller. Remember, 2 is acceptable. If you substitute in 2, you get 6 plus 4, 10, which is less than or equal to 10 because it's equal to 10. Okay, let's try some more. Three x plus 5 is less than 5x plus 9. Okay, now we want to isolate x. Okay, let's start by, say, subtracting 5x from both sides of the inequality. Remember, that's perfectly acceptable. We are subtracting. That's fine. You're allowed to subtract the same quantity from both sides of an inequality. Okay, remember, our aim is to say get all the terms with x on one side, all the constants on the other. Okay, this gives us minus 2x. 3x, take away 5x, that's minus 2x plus 5 is less than 9. Now I'm going to subtract 5 from both parts. Giving us minus 2x is less than 4. Right. Now we would like to divide both sides of the inequality by minus 2 so that we can get x alone. Okay, that's when you have to be careful. Okay, you're allowed to add the same quantity to both sides or subtract the same quantity from both sides. That's fine. When it comes to multiplication or division, okay, by a positive number also you don't have to worry. But if you multiply or divide by a negative number, then you reverse the direction. So we have minus 2x and 4. We would like to divide both sides by minus 2. If we do that, we must change the less than to a greater than. We must reverse the direction of the inequality. Okay, right here, we're going to reverse the direction of the inequality. Okay, now minus 2x over minus 2, of course, is just x, is greater than, and be careful, you had a plus 4 divided by a minus 2, that's minus 2. The final answer here, all x values strictly greater than minus 2, would make this original inequality a true statement. Okay, let's try another example. 3 minus x over 2 is less than or equal to x over 3 minus 2. Okay, and for the first time, we see an inequality with fractions. Well, you know how you'd solve an equation with fractions. You would first try to multiply both sides of the equation by the lowest common denominator. In other words, multiply both sides by a number that would clear fractions. And we're going to do the same thing here. In this particular case, we have halves and thirds. We have 2 and 3 in the denominator, and the lowest common denominator is 6. So what we're going to do is start off by multiplying both sides of the inequality by 6. Now, 6 is a positive number, so we can keep the same direction on the inequality. This will get rid of all the fractions, and then we'll have an inequality like the ones we had before, and we can solve it the usual way. We'll multiply both sides by 6 and keep the direction the way it was, less than or equal to, because 6 is a positive number. Okay, now we're going to use the distributive law. We're going to have here 6 times 3, take away 6 times x over 2. Okay, don't forget you have to multiply the 3 by 6 and also the x over 2 by 6. Less than or equal to 6 times x over 3, take away 6 times 2. Now, 6 times 3, that's 18. 2 goes into 6 3 times, so we have minus 3x less than or equal to, now 3 goes into 6 twice, so 2x minus 12. This is 6 times 2 here, in case you can't see it clearly. All right, let us add 12 to both sides of this inequality, giving us 30. 18 plus 12, that's 30, minus 3x less than or equal to 2x. And now let's add 3x to both sides, giving us 30 less than or equal to 5x. Well, you don't have to isolate the variables on the left. Okay, in this particular case, we have the constants on the left, the variables on the right. That's perfectly okay. We're at the point where we have 30 is less than or equal to 5x. Okay, we can now divide both sides of the inequality by 5, which is a positive number. We can keep the same direction. If it was a negative, I'd have to cross this out and write a greater than or equal. And 30 over 5 gives me 6, less than or equal to, the 5's cancel, 6 less than or equal to x. Okay, which is perfectly acceptable, except I feel a little more comfortable writing it the other way, x greater than or equal to 6. In other words, where are those values that make this original inequality a true statement? Okay, the original inequality up here. You can plug in any value 6 or greater, and it will make the original inequality a true statement. Okay, if you try values that are less than 6, it will not be true. Okay, and let's try one more example. I want to show you how to solve a double inequality. Okay, minus 2 less than or equal to 3x plus 4 less than 13. Remember, this is minus 2 is less than or equal to 3x plus 4, and 3x plus 4 is less than 13. And minus 2 less than or equal to 3x plus 4 means the same as 3x plus 4 is greater than or equal to minus 2 and less than 13 at the same time. Want to know where are those x values? Okay, so that 3x plus 4 will be between minus 2 and 13, possibly equal to minus 2, but strictly less than 13. Okay, now what you're going to do is operate on all parts of the inequality at the same time. In other words, you're going to subtract 4. We will subtract it from all parts of the inequality. Remember, our idea, once again, is to isolate x, but this time we want to isolate x in the middle. So let's subtract 4 from all parts of the inequality, giving minus 6 less than or equal to 3x less than 9. This was a strict inequality. This was a less than or equal. Okay, now we can divide all parts of the inequality by 3, which is a positive number. All right, we're allowed to do that. Keep the same directions, giving us a final answer, minus 6 over plus 3. That's minus 2 less than or equal to x less than 3. So where are those values for which this is a true statement? Between minus 2 and 3, possibly equal to minus 2, but strictly less than 3. Substituting any value for x between minus 2 and 3, like this, will make this one a true statement. Okay? If you want to sketch the graph of the inequality here, we could have 1, 2, 3, 4, minus 1, minus 2, minus 3. I want everything from minus 2, including minus 2, up to, but not including 3. So I will put a circle here and not fill it in. This indicates starting at minus 2, everything between minus 2 and 3, including the minus 2, but excluding the 3. And this brings us to the end of the videotape.